Hello everyone, welcome to this session. Today I would like to represent my current research work to you, increment learning. What's increment learning? Increment learning is a machine learning paradigm that focuses on incrementally or continuously updating and expanding an AI's knowledge and capability over the lifetime. ChatGPT is a perfect example of an AI model that utilizes the increment learning. From 2018, OpenAI released the generative pre-trained performance GPT model known as GPT-1. To now, GPT-4 becomes more aligned with users' input and can handle a wide range of tasks. Increment learning allows ChatGPT to evolve and improve its conversational ability continuously. Since it continuously updates and expanding, the increment learning is also called continual learning or continuous learning. It is also called lifetime learning. The concept is mimicked to humans. Our humans are able to incrementally learn the knowledge throughout our lifetime, from childhood to very old age. Also, in some traditional scenario, it means online learning, like an online system constantly receiving streaming data and improving its performance. To understand incremental learning, first we need to know how AI actually works. The modern AI uses technology called machine learning. Machine learning is a branch of AI that deals with development of algorithms and models that allow computers to learn from data and improve their performance on a specific task. It involves teaching computers to automatically identify the patterns, extract meaningful information, and make predictions or decisions based on that knowledge. Machine learning algorithms learn from a given dataset, which consists of input features or corresponding target values or labels. By analyzing the patterns and the relationship within the data, machine learning algorithms can generalize and make predictions on new unseen data. Recently, the machine learning trends to use deep neural network, consisting of a big network of nodes. Each node parameterized by a weight theta. To learn is or to train a neural network is to find a bunch of optimal weights that makes accurate generation, prediction, classification on text, video, graphics, and speech audio. Why increment learning is so important for AI? Here I give you an example in the AI industry. Once I was working in an autonomous driving company, ComCar. Our initial task is to train an object detector which can locate vehicles. We got the traffic data and manually annotated the vehicles. By sending vehicles to the AI model, for example YOLO, the model learns to develop a capability of detecting vehicles in images. Couple of weeks later, we got another task that it must detect the bicycles on the road. We can use the same procedures to learn to detect bicycle, but the question is how to make a detector can detect both vehicles and the bicycle. Here's solution 1. To run above two models together and combine two results. This solution works, but it makes AI running slower if more objects are required to be detected. Solution 2. To combine two datasets into one dataset and do the learning procedures to train a new model. It also works, but the learning costs much time. Hence, these two solutions are no good. And here is incremental learning. We start in the increment 0 with the standard machine learning to train a model for vehicles. And in the increment 1, we learn a new model upon the established model with additional bicycle data so that the new model can detect both objects. The learning upon is called fine-tune. Later on, each increment, each new capability is added and updated. In increment n, we fetch the traffic sign data into the last model. The model has not only the capability of detecting vehicles and bicycles, but also other capabilities like traffic sign recognition. However, increment learning faces a big problem: catastrophic forgetting. It is a phenomenon that a model lost the ability to perform old capability after learning new capabilities. It's very much like our human beings. We are able to incrementally learn knowledge through our lifetime, while we do tend to gradually forget the previous knowledge over the time, especially when grasp new knowledge. Catastrophic forgetting happens a lot in machine learning, especially in neural network, because neural network must frequently adapt to weights for newer increments. For example, we had a neural network which is trained to recognize birds, dogs, and cats, which is the increment 1. We then train it with other classes such as dolphins, lions, and rabbits, which is the increment 2. After some time, the neural networks can start getting poor results on recognizing any class in the increment 1 because the weights are adjusted and biased to recognize the classes in the increment 2. To overcome catastrophic forgetting, we use dynamic network, which create new subnetwork for each increment. All subnetworks are concatenated into a final network for preserving the previous knowledge. However, it encounters two problems. First one is continually increase network parameters. When more increments are coming, the network becomes large. Second, is no sharing of knowledge between the network. Hence, we propose our approach: SCREAM, knowledge sharing and a compact representation for class increment learning. We first frozen the old model and create a new model with the same size for learning new increments. Then, we employ balanced decoupling knowledge distillation to compress old and new models into a compact model. In the next increment, the compact model becomes the old model to be frozen, and a new model is generated. It's in this iterative frozen state mode, the size of the dynamic network stop expanding and remain constant, and the representation become impact. The clustering module for knowledge sharing by separating new class far away from old classes. To validate the performance, we utilize three commonly used public datasets: CIFAR100, ImageNet, and TinyImageNet. As shown in Table 123, our approach achieved the best performance in the vast majority of scenarios. We conduct extensive experiments. Its figure illustrates the accuracy of our approach compared to other SOTA in different scenarios. It shows that our approach not only maintains high accuracy, but also addresses the issues of network structure expanding, ensuring the efficient utilization of system resources. As we look ahead, there are many exciting areas for future research in incremental learning for you can explore. Let's highlight a few potential directions. For example, in large language model, computer vision, especially autonomous driving and UAVs, medical diagnosis, and financial market analysis.